Hello, everyone. We are back after the lunch for the lightning talk with Yedidya Schwartz. Hello, Yedidya.
Hey, how are
Hi,
you?
good to have you with us. You are currently a software architect and DevOps lead at OwnID, and yeah, look back at more than 12 years of experience. So the stage is all yours. I don't want to steal more of your time. So see you later for the Q&A.
Thank you. So, hello everyone. Thanks for joining. My name is Yedidya Schwartz. I'm a software architect and DevOps lead at OwnID, and for the past almost 2 years, I am at OwnID. I'm here to talk with you about our architecture refactor and how we took our product loading time performance to the next level. A few words about me before we start. So at OwnID, I am leading the infrastructure domain, designing and implementing new features, dealing with observability, performance, production health, etc. Before my current role, I was a tech lead at WalkMe and the commander in the IDF Army Intelligence. I'm a certified AWS solution architect, and I'm holding philosophy BA and MA degrees. What should you expect from this lightning session? So I will start with the problem we had and what we wanted to solve, then a short theoretical part where I will cover two design patterns that were my inspiration to come up with a solution. I will cover a real case study that I designed, implemented, and tested at OwnID, the small startup where I work, and we will dive into the architecture implementation details. And at the end, I will give you some practical takeaways. So to give you the context of the technical aspect of the session, 20 seconds about our product. So we are a web-based authentication solution. Our mission is to increase the identified users in websites. We are using passwordless solution, leveraging FIDO2, WebAuthn API, passkeys, QR codes, OTP by emails and SMS, and many more authentication magics. And now to the problem. That's how our product looks like in the common variation. It's a biometric icon button. You can see it, it's part of the login form. That widget must look native as part of the website. It can't be loaded with any delay. Although it's an external product, it should look like it was original with the website itself. We experienced issues around it. From time to time, the widget was loaded with a huge delay, and sometimes it wasn't loaded at all. It was blinking. You can see that for 1 or 2 seconds it wasn't there, and then it suddenly showed up. It doesn't look good. Our product is accelerating the authentication process, but the performance of what happens before and after to the core process is also a part of the end user experience. Yeah. And if you want to accelerate the full authentication experience, we must be with the top performance on every part of the flow. So as we are serving many big brands, we need to be in their performance, to be in their scale. We should support all their impressions. We have multi-tenant architecture in our product, and our servers need to support on peak times tens of thousands of end users that are loading our product in the same second. So now, once the point we want to improve is clear, let's dive in. That's what we had at the end of 2022. These are the requests that had to be sent from the browser in order to load our widget. Translation files, our SDK, dynamic configurations from the server, all the requests are made to a CDN, to several CDNs that reference S3 buckets for static files that AWS storage service, or a load balancer for dynamic requests that goes to a service that requests the database. This solution had a high latency, request dependencies, and there was no doubt that it needs to be improved. We decided that we don't want a short-term solution as a plaster, but a bombastic solution with top-level performance that will stay with us for the long term while we are growing as a startup. So now let's move to a short theoretical part. I want to cover two design patterns that were part of the inspiration to the solution. The first one is Materialized view pattern. In computing, a Materialized view is a database object that contains the result of a query. And if we think about restaurants, for example, in McDonald's, the orders are provisioned in advance. What it means, it's a complicated query that contains meat, tomato, sauce, bread, fries, I don't know what else, that are all waiting for you as a customer in a box to order them. That's how in a few very good McDonald's branches, you may wait only 1 minute to get your food. This design pattern is being used, for example, to store the results of a complex join query, a result of a query on a huge amount of data, or a query from multiple slow data sources. X, for example, they are using this approach to hold your feed ready in advance. So when you open the app, you get it very, very fast. The second design pattern is server-side composition. Let's assume you have 3 different front-end components and the browser performs 3 requests to load each one of them. This design pattern brings the idea of performing 1 request to load all of them at once. You need to add a proxy server that merges the components into one file, a JS or HTML file, and then returns it to the browser. There are many out-of-the-box products for this proxy, such as Podium, Nginx module, and more. That's all for the theoretical part. Now let's convert it to something practical that we can use. So our requirement checklist has 5 bullets. That's a well-defined list of technical requirements that we agreed about before starting the architecture planning. First, we want our resources queries to be super fast. The dynamic configurations and the static files, everything needs to be loaded super fast. Secondly, we want to merge all the requests into one. We want to reduce the failure rate. Less network requests, the less changes for a corrupted load of the widget. The widget needs to be loaded together with the website, okay, as close as can be to 0 milliseconds of latency. It should look native and not like a third-party service. The mechanism should support a huge request scale, tens of thousands in a second on the peak time. And the last requirement is the response from the server must always be as updated as possible. This means that if one of our customers decided to change the widget color from red to green, so in 1 or 2 minutes, we expect all end users of this customer to see the widget in the new color. So as we saw, that's how the widget loading architecture used to look like before the process. This is the first step of the new architecture. We are preparing all the resources, dynamic and static, under the same data source. Config server rigs the data from the various origins and writes it into Redis in a specific predefined structure. The component that is going to consume the resources from Redis on the next step that I will show you will be able to do it super fast. Instead to go to the S3 buckets and download it into the database and the services, it just reads it directly from Redis. That step answers the first requirement. As I said, the next step is consuming the resources from Redis. That's the responsibility of the baking server. That is kind of the core of the solution. The single concern of this microservice is to get a client ID and return a JavaScript file that has all the required resources and the data to load the widget for that app. Translations, configuration, SDK, and etc. The logic in high level is split into 3. First, we create a template of the output with placeholders instead of the actual resources. Then we read all the relevant values from Redis of the resources that we baked in advance in Redis. And then we just replace the placeholders with the actual data from Redis. That's an example of an output file. You can see everything merged together. So this was the baking server. It covers the second requirement of merging the requests into one. Now, the baking server is becoming the new bottleneck of this architecture, if you think about it. On peak times, as I said, there may be tens of thousands of parallel requests. Our server won't handle this load. It has an auto-scaling mechanism, but it will happen too fast, and the request may be denied. So the solution for this is a CDN between the browser and the baking server. I want to give you a short brief of a CDN in the way that I look at it in terms of this solution, in the way that it solves our performance challenge. A CDN, a content delivery network, is mostly known for performance boosting of static files loading. Instead of one main server, it gives you a distributed servers network. If you are from Israel, you will get the data from Tel Aviv, but if you are from Brazil, you will get the data from Sao Paulo. Okay, every local server is called an edge location, and the main server is called the origin. The edge location can store everything, and the origin can be an S3 bucket, a server, or another AWS service. The first request to an edge location to get a specific file will trigger the fallback. So the request will move forward to the origin server. On the second request, the file will already exist in the edge location, so the origin won't even know that the request was made. So instead of getting the widget from the baking server, the CDN will handle most of the requests, theoretically one per edge location. And AWS has something like 400 edge locations, so baking servers should be capable to deal with it. Now I want to challenge this solution. Let's say that one of our customers sent a marketing email to its 20 million end users, and in the email it says the first 100 people to log in into the website and fill the form will win $1,000. So let's say that the relevant file for the widget doesn't exist at the moment in the CDN. And what will happen is that at the same second, tons of end users will want to log in to win the prize. So they will load the widget all over the world. All the requests will reach to the CDN, and the CDN won't have the required file on the edge locations. And then baking server will get tons of parallel requests in a huge peak and won't be fast enough to scale. End users will receive 500 status for the widget request, and they won't see the widget and won't be able to log in with our product, which is very bad. That's why Cloudfront CDN has a built-in feature that's called request collapsing. If there are parallel requests to the same object, Cloudfront sends to the origin only the first request and pauses before forwarding the additional request to the origin. This pause helps to reduce the load on the origin. Cloudfront sends the response from the original request to all the requests that it received while it was paused. And to make sure that the CDN behaves as we expected, once we went live on production with one customer, I opened the Cloudfront reports page on AWS console. That's one observability tool that we have. It's a built-in observability tool in AWS. So for each file, you can get statistics. How many requests were performed? How many of them hit the cache successfully? How many of them missed the cache? Which means the requested file didn't exist in the edge location and the request was fallback to the origin. So what we saw is that in a week, I found 253 misses, which means 253 requests that reached to the baking server for that specific customer. Then I double-checked this number to make sure. We have, as an external monitoring tool, we have Datadog. The APM tool inside Datadog, the application performance monitoring, it counts every request to our servers. So I filtered the request to the specific file and found 249 requests. The numbers are close, as I expected, so everything is okay. So at first, we thought that we made it and our bombastic solution can suffer every load, but then we started to roll out the solution to more and more customers. And a few months later, we started to notice errors coming from Redis. An error means that the end user doesn't see the widget at all. After investigation, we found out that we crossed AWS Redis network allowance limitation from time to time. We had the hotkey problem. You can go and read about it if you're not familiar with it. It's something very interesting. The thing is that too many Redis requests that were sent to the same shard, okay, because it was a specific customer that has a huge scale. To tackle this issue, we had to reduce the requests that are performed to that specific Redis shard. So we tackled the issue in three different ways. First, we sharded out the key that caused the issue. We created the same key 100 times in different shards, in random shards. So each time it will be read from a different machine, okay? Secondly, we added an in-memory cache before Redis in baking server, another level of cache. And finally, we also leverage an extra Cloudfront feature that exists exactly for such cases, which is called Origin Shield, which I won't elaborate about it, but you can go and read about it. That's a screenshot of the APN traces while testing the baking server in memory new cache on a specific file. So the first request at the bottom went to the database to retrieve the data since it wasn't exist even on Redis. That's the worst fallback that we have. Second request could take the data from Redis, and third and fourth request took the data from the in-memory new cache. So let's summarize the protection layers we have to load the file. First, we have the CDN edge location, then request collapsing mechanism, then we have the regional edge cache. That's an extra layer inside Cloudfront CDN architecture. Then we have the origin shield, the in-memory cache on the baking server, the Redis cache, and if all the 6 protection didn't help, the data is loaded into Redis from the database by another microservice. So as Cloudfront supports 250,000 requests per second, we are okay with this solution for now. The scale requirement is checked. Now the last requirement, keeping the data updated all the time. If the customer updated configurations, all end users should be affected in not more than 1 or 2 minutes. To achieve this, we leverage a mechanism that already existed in our architecture, Redis PubSub. This is actually a messaging mechanism over Redis using publishers and subscribers. Since this is a lightning session, I won't have time to elaborate about this implementation. Very shortly, I can say that it triggers a CDN invalidation and rehydration of data into Redis. You are welcome to read about it in our engineering blog that I will reference in 3 minutes at the end of this lecture. So the last requirement is also met. And after all the process was finished, that's how it looks in the network tab. I refreshed the same website 4 times. For the first time, there was a fallback to the baking server. After that, the file was fetched from the CDN from half second to 14 milliseconds. That's an improvement of hundreds of %. The legacy loading approach was still functioning when we moved to the new mechanism. The solution was gradually rolled out. That's what allowed us to find performance issues and tackle them before they affect all our customers. The design patterns we talked about come into action on these parts of the architecture. You can argue about it, since every design pattern can be expressed in many aspects, but that's how I see it. We are materializing the possible combinations of the data in Redis, and we are compositing the components using baking server. I want to summarize with a few takeaways you should remember if you are planning to refactoring process, performance improvement, or any feature that will require a massive architecture change, okay? First, the proposed solution was designed in light of the existing architecture. We leveraged config server, Redis PubSub, and more components that already exist. If you can, avoid from new infrastructure components to maintain. Don't be afraid to change key decision of your solution architecture during the development process. It's better to change early than stay with the problems for years later. For example, we talked about storing all the baked files on S3 buckets, and then we found the problem with this approach after we started to develop it. So we totally changed the solution and start almost everything from scratch. Don't start anything if you don't have the proper monitoring and observability tools. I can't even imagine how many production issues we would have without the powerful monitoring tools we used. Maybe we wouldn't even know about the production issues, which is worst. And design patterns are for inspiration. That's how I see it. Their implementation is very flexible. The design patterns need to serve us we shouldn't serve them. Don't be design pattern oriented. See how they can open your mind and then utilize them in your style. And boosting the main process that uses the core technology of your business sometimes depends on processes that come before and after. The user experience is an overall experience, even if the passwordless experience itself is amazing on our product. If it's not loaded on time or not loaded at all, it's not good enough. Okay. So that's all for today. I hope you learned something new and that I open your mind in some way. You can read more deeply about the process that I just described in an article series that I published in our engineering blog. And thank you very much.
Thank you very much, Yedidya, for this short but insightful talk. It seems like the audience doesn't have any questions, but yeah, I'm sure everyone enjoyed it. So
It was clear.
thanks again
Thank you
for being with
Thank
us.
you.
And yeah, please, everyone, don't forget to give your feedback when you leave the stage, and enjoy the rest of the day.
Thank you. Bye-bye.